Welcome back. So in this chapter, Thermochemistry, we're going to talk about how heat is related to chemical changes. So heat, thermochemistry. And as we get started here, we need to talk a little bit about heat as a part of a chemical reaction, how we can track it, and so forth. So first of all, when a chemical reaction takes place, there is an energy change. This is a fundamental truth in chemical reactions. And in fact, the only reason that chemical reactions take place at all is because there is an energy change associated with the chemical reaction. Generally, chemical reactions take place because the chemical substances are becoming more stable as products than they were as reactants. But not always. Sometimes they become less stable, and we can track that in a couple of different ways. So the first law of thermodynamics, we want to write this out because this is going to underlie a lot of our consideration moving forward. The first law of thermodynamics, and you may remember that we talked about this in an earlier chapter when we were discussing electron relaxations from a higher n level to a lower n level, quantum level. And we said that energy can be converted between forms but energy cannot be created or destroyed. So if you have energy, it can be converted between different forms of energy, but the energy cannot just be created or destroyed. It has to go somewhere. It can't just disappear, and you can't just poof, create energy out of nothing. There had to be energy there to begin with. So with that in mind, one of the types of energy that we can talk about is heat energy. And we represent heat energy as with the lowercase q. And heat energy is the energy associated with the motion of a substance's particles. So another way of saying the motion of the substance's particles is the vibration. So within each substance, for example, if you had a lump of sugar here on the table here, even though the lump of sugar is not moving around, the individual sugar molecules, the sucrose molecules, have some heat energy in them, and they are vibrating on some molecular level. And that vibrational motion is what we call the heat energy of that substance. There is a more specific term that we use for heat energy, and that is enthalpy. Enthalpy, E-N-T-H-A-L-P-Y. And enthalpy is abbreviated with a capital H. Enthalpy. That is a specific word that we use to describe the heat energy when we are talking about a chemical reaction. So, when we are exchanging heat from one substance to another, for example, from my hand to the paper, there's heat energy being transferred. There's not a chemical reaction between my hand and the paper. So that is just transferring heat, which is the lowercase q. But if I were to burn the paper, then I'm running a chemical reaction. And the heat that it would be given off would be enthalpy, because that's the heat energy in a chemical reaction. The change in enthalpy, the delta H, delta meaning change, capital H meaning enthalpy. The change in enthalpy is the heat that is exchanged from a reaction system to its surroundings, and we are assuming that we are at constant pressure when the chemical reaction takes place. So when you run a chemical reaction and let's say, for example, heat is given off, say you're burning paper, and the heat is given off, then the paper molecules are losing their heat energy to the outside surroundings. And so we say that the paper is undergoing a change in enthalpy as it's undergoing that combustion reaction. So let's talk a little bit about what we mean by system and surroundings. Let's imagine that I have some chemicals and they are going to react. I'll represent some of the molecules in blue and some of them in green and maybe a few of them in red. So let's say I have 3 reagents here. And I've mixed them all together, and those are the chemicals that I've mixed together. And these chemicals start to react. And as these chemicals start to react, they give off heat. So as the chemicals react, they are giving off heat. Where are they giving off heat to? They're giving off heat to the surrounding atmosphere, maybe the air around them. So the system here refers to the chemicals that are reacting. That's the chemical reaction. And the surroundings refer to the area or the universe around the system. That surround that system. So we can talk about heat being transferred from the system to the surroundings. And notice this is heat would be Q, which would also be an enthalpy if it's talking about a chemical reaction. So we can talk about heat being given off from the system to the surroundings, or we could talk about heat being taken in, absorbed into the chemical reaction from the surroundings, in which case heat would be going in the opposite direction, from the surroundings to the system. Well, let's think about what this means. If we have a system that is giving off heat, then heat is a product of this reaction. In contrast, if we have a system, a chemical reaction, that is absorbing heat, taking in heat from the surroundings, then heat would be a reactant of this reaction because we're having to add heat to this reaction as one of the components on the reactant side. So there are a couple of different ways that we can represent this with a graph. So that's what we're talking about here. Heat, or enthalpy, can be treated either as a reactant of a chemical reaction or it can be a product of a chemical reaction. And the easiest way to see this in graphical terms is to write a little graph called a reaction coordinate diagram. So I'm going to draw 2 of those. One of them where heat is a reactant, and the other where heat is a product of a chemical reaction. So let's draw a little y-axis and an x-axis here. And on the y-axis, I'm going to put enthalpy. That's the heat of the system as it is reacting. And then on the x-axis, we are going to show the progress of a reaction. As the reaction in time continues on, we're going to track to see what happens with the enthalpy. So somewhere at some level up here, we're going to put the reactants. So the reactants of this reaction have some enthalpy, some heat energy in them. For example, the sugar cube I talked about earlier, or the piece of paper before it starts to react. That reactant has some heat energy in it before it starts to react. And then, as the reaction occurs, if heat is a reactant, then I'm going to be adding heat into a system. And so the final condition of the products will have a total enthalpy or heat that's higher than it started out as. And that means heat was a reactant. Heat was a reactant, so we added heat into the reactants, and we ended up with products that had more heat in them. Now, you may not understand what I'm doing right here with the little bump. That just means that there's a little bit of a barrier for this reaction to take place. So it has to get over that energetic barrier and then form the products. So again, heat is a reactant in this case. So we start out with our other reactants, our other reagents of the reaction, and we add heat to them on the reactant side, which means that when the reaction is completed, the products have had heat added to them. Now, let's take a look at some consequences of this. If this is the final condition right here, the final enthalpy, and this level right here was the initial enthalpy, then the change in enthalpy is that gap right there. We started here with this much enthalpy, we ended here with this much enthalpy. The delta H is here. And since we know that to calculate deltas, delta H equals the enthalpy final minus the enthalpy initial. And since the final number is a larger enthalpy than the initial number, then we know that whatever this number is, it's going to be a positive value because the final is larger than the initial. So when we subtract the initial, we're going to be left with a positive number. So the delta H is positive for this reaction. Overall, we have increased the enthalpy of this system. Heat is a reactant. Well, when heat is a reactant and the delta H for the reaction is positive, we have a term for that, and we call it endo, E-N-D-O, thermic. Endothermic. Endo means going into. So that means endo, into, thermic, heat. So heat is going into the system. Heat is a reactant. It is being added to the system. Now let's contrast that with the other situation where heat is a product of the system. Well, let's draw our reaction coordinate diagram again. We've got enthalpy on the y-axis, and we're going to track the reaction as it progresses. We don't know exactly what enthalpy our reactants have, so I'll just put them there. They have some enthalpy in the reaction. And now if heat is a product, that means heat is being given off by this system. If heat is being given off by the system, then the products are going to have less heat in them than when they started. So we'll connect these with a little bit of a transition here to show that there's a little bit of an activation barrier for the reactants to react to form products. But again, heat is a product of this system. As this reaction occurs, heat is going to be given off so that the products have less heat in them than when the reactants began. Again, we can take a look at the change. If this level now was the initial enthalpy, and this level is the final enthalpy, there's our delta H, change in enthalpy for this reaction. Again, we know that delta H equals the final enthalpy minus the initial enthalpy. And now notice that the final enthalpy is a smaller number than the initial. So when I do final enthalpy minus the larger initial enthalpy, I'm going to give a negative number here. Well, when heat is a product of a reaction, and the delta H, the change in heat for the whole system, is a negative value, the word that we have for that is exothermic. What does this mean? Exo meaning exiting or going out. Thermic, heat. Heat is going out of the system. So this is the case where we have heat being given off by the reaction. So when I drew a system reacting up here, like a piece of paper burning, it's giving off heat to the surroundings. Which of these two cases represents burning paper? Is burning paper an endothermic or an exothermic process? Well, hopefully you said that it's an exothermic process. Yes, we may need to help get it started by adding a little bit of flame to it. And that's what that little bump represents right there. We have to kind of help it get over that bump, that little activation barrier. But once we do, that paper, as it burns, is going to generate products that have a lower heat enthalpy in them, and therefore that heat has to go somewhere, right? So if the paper ends up becoming products, combustion products with less enthalpy in them, where did the heat go? Well, according to the first law of thermodynamics, energy can be converted between forms, but it cannot be created or destroyed. So when paper burns, what is happening is we are converting some of its internal chemical energy to the heat that we feel being given off into the surroundings. So there again, we have a delta H that is negative because the system is losing its heat energy. That's why delta H is negative. Because the system is losing its energy, we say it's exothermic. The heat is leaving the system, and therefore heat is a product of the reaction. Okay, let's just fill in a couple of gaps here. So a few gaps so that we have this documented in our notes. When heat energy is absorbed into the system from the surroundings, then heat is a reactant. We call this process, what do we call it? It's endothermic. And the delta H is what value? Is it positive or negative? It is positive because the system is gaining heat. It's absorbing heat into the system, so it's positive. In contrast, when heat is being given off from the system as it reacts to the surroundings, then heat is a product of this reaction, and we call this process exothermic. And the delta H for an exothermic process is negative because the system, the chemical species, are losing their heat. They're giving it off into the surroundings. Well, let's think about what this means. Heat can be a reactant, or heat can be a product of a chemical reaction. If heat is a reactant or a product of a chemical reaction, then can we do stoichiometry on heat the same way that we do stoichiometry on chemical substances? And the answer is yes. And that's what this next section is doing. The stoichiometry of heat. Since enthalpy, remember that's enthalpy is the heat of a chemical reaction. So since enthalpy can be a reactant or a product of a chemical reaction, then yes, stoichiometry calculations can be performed on the heat too. So I'm giving you a sample problem here, and this is a stoichiometry of heat problem. says, given the following balanced chemical equation for the burning of methane gas, and here it is, and the change in enthalpy given for the reaction, it's right here, delta H equals negative 890.4 kilojoules of energy per mole reacted. So we've been given a change in enthalpy, and it's saying it's a negative value. So does that mean this is exothermic or endothermic? It's exothermic, isn't it? The system is losing heat energy. Where's the heat energy being given off? It's being given off into the universe, into the surroundings, and so it's losing its heat energy to the surroundings. So it's giving off heat. Heat is a product, so it's got a negative delta H. And that's how much energy it's losing per mole of reagent that's reacted. So, questions here. A, what is the enthalpy change, that is, what is the delta H, when 12 grams of methane are burned? And B, how much heat is released? So let's deal with question A. What is the enthalpy change when 12 grams of methane are burned? So what are they asking for? They are asking for an enthalpy change. They want how much energy is being changed, either gained or lost, when 12 grams of methane are burned. Well, when I see a delta H given for a chemical reaction, you may notice that that's a derived unit, kilojoules in the numerator and moles in the denominator. Let's write that a little bit differently so that it's really obvious. Negative 890.4 kilojoules per 1 mole. And when I write it like this, as a numerator-denominator, I hope it becomes more obvious that this is a conversion factor. So a delta H for a chemical reaction is a conversion factor. And look what it converts between. It converts between moles of a chemical substance and some amount of energy in kilojoules. So now as we start to think about this, I would like for you to try to do this problem yourself and answer part A. What is the enthalpy change? So you're going to be solving for kilojoules. So that's where you're going to be solving for. You're going to get an answer in kilojoules. That's the enthalpy change when 12 grams of methane are burned. So we're going to start with 12 grams of the methane, CH4. So I would like for you to pause the video and see if you can complete and answer this part A. This is part A right here, right? See if you can answer that. Go ahead and pause the video and give it a shot, and when you're done, you can come back and I will finish that one up for us. Okay, let's come back to this and take a look and see what we can do to get from here to there. The question is, what is the enthalpy change? They're asking for an energy. That's what enthalpy is, right? When 12 grams of methane are burned. So that's where I'm going to start. I'm given a quantity of methane, but look at our endpoint. We are not trying to find another chemical substance. We are trying to find a heat. So for the first time since we started doing stoichiometries, the heart of our stoichiometry problem is not going to be a mole-to-mole conversion. It's going to be a mole-to-energy conversion. And that's what we do when we do stoichiometry of heat. We can do mole-to-energy conversions as the heart of our stoichiometry. So with that in mind, I'm thinking about the kind of conversions that I'm going to need to get to energy. If I can use this as a conversion factor, then I can get to energy and have this as my very last step in my dimensional analysis. To do that, I need moles of this chemical substance. And to get there, I need to be able to convert from grams to moles. So I think my first conversion step is going to be grams of methane to moles of methane. And that allows me to convert into moles of methane. Then my next step would be to convert from moles of methane to what? From moles of methane to what at this point? Well, it looks like, goodness gracious, it looks like I'm done. I only have one more conversion to do and I've got energy, don't I? So from moles of methane to kilojoules, right? So I've converted from grams of methane to moles of methane to kilojoules, and I've got my answer. So we know that molar masses are 1 mole. We know that this conversion is right over here, so I can go ahead and put in those numbers, negative 890.4 over 1. And what goes here? Well, this is the molar mass of methane. Let me calculate that quickly. 16.04 grams for 1 mole of methane. And that's 890. And with a negative, don't forget to bring the negative sign down. All right. So now I have this math, and I know that I can cancel out my grams of methane. I can cancel out my moles of methane, and I have kilojoules. And that kilojoules is an energy, and that's what it's asking for. What is the enthalpy change, which is an energy? So let me do this math. And my calculator gives me an answer, and it is a negative 666.135 and so forth. But notice I have to round it to 2 sig figs, so that is a negative 670 kilojoules. Is that answering my question? Let's see if that makes sense. The math works out, but let's see if it makes sense. Up here I was told that for every mole of methane that reacts, I have a negative 890.4 kilojoules. That is, this system will give off that much heat for every mole of methane that I react. 12 grams is not quite a whole mole of methane. A mole of methane would weigh 16 grams. So I'm only using 12 grams. I'm burning 12 grams, so not quite a whole mole of methane. So I should release not quite all of that energy. And so it does look like it's in the right ballpark. It's a negative answer here. The negative answer. Why is the negative answer meaningful? Because it is asking for an enthalpy change. The change. And the enthalpy change for this reaction is the reaction, because it is exothermic, it is going to give off heat, and therefore the change in enthalpy for the reaction should be a negative value, because this reaction system is losing energy. So there is my delta H for the reaction. And the way we abbreviate reaction is RXN. So the delta H, the change in enthalpy, that's what it was asking for. For this reaction, given that amount, it is changing by a negative 670 kilojoules. What does that mean? It's losing 670 kilojoules, or it's giving off 670 kilojoules. Well, let's answer this part B, because we just did. How much heat is released? Well, we just decided that the delta H for this system is a negative 670 kilojoules. So how much heat is it releasing? It's releasing the positive amount of that. So a positive amount of 670 kilojoules. Now I don't have to put the positive there. It's understood to be there if I just leave it off. But I want to put it on there to emphasize that, again, you can calculate a change for a system, and then when you're asked how much heat is released, it's going to be the opposite sign of that. Remember when we were dealing with electron relaxations and the atom itself might have a negative change in energy? But then when we asked, okay, well, how much energy is being released into the universe? It's a positive amount of energy that's being released. You might remember the analogy that I used. If I give you $10, then what is my change for my system? My system change is a -10. How much money have I released? I've released a positive amount of that, so it's a +10. So there we go. We've done a stoichiometry of heat. Two important factors to remember. First of all, to do a stoichiometry of heat, you can think of heat as either a reactant or a product of a chemical reaction. And if that is the case, then as a chemical reaction takes place, the change in enthalpy for the chemical reaction will either be a positive or negative number. The delta H, the change in enthalpy for this reaction, is given as some energy, positive or negative, per 1 mole of reactant reacting. And when you are given that delta H, you are being given a conversion factor. That conversion factor will allow you to convert between moles of a chemical substance and joules or kilojoules of heat energy. With that in mind, we can set up a dimensional analysis to solve for the stoichiometry. And normally we would have gone through the heart of a stoichiometry, which would have been a mole to mole conversion. But in the stoichiometry of heat, we are now converting between moles of a chemical substance and joules or kilojoules of energy. Okay? So this is the first time that the heart of our stoichiometry is changing. It's no longer a mole to mole ratio, it's a mole to energy ratio. Because heat is not a chemical substance, it is an energy, a form of energy. Okay? All right, there we go. There's an example of a stoichiometry of heat problem. One quick comment here. I just want to recall from our previous study, when we were talking about temperature in gases, I made a special note about temperature, that the temperature is a measurement of, or it's related to, the statistical average of the thermal or vibrational energy in a sample. You recall when we had a sample of a gas, and we said that in that sample of a gas, there are gas molecules with some high thermal energy, there's some gas molecules with low thermal energy, but the temperature is related to the average of the thermal or vibrational, or another way to say it is kinetic energy, within that whole sample. So there's a distribution of thermal, vibrational, or kinetic energy, and temperature is just related to the average energy. So at a given temperature, some particles will have greater vibrational energy and some will have less vibrational energy. And you may recall that we had a little distribution graph so that we had the number of particles, and then we had the energy, and we had some particles, a small number of particles with low energy, and if we graphed it, we'd have a lot of particles with some medium amount of energy, and then we'd have a very few number of particles with a much higher energy, and then the temperature is related to whatever the average is. I wanted to take a moment to remind you of that, because temperature is not the same as heat. So temperature is not equal to Q. Temperature and heat are not the same thing. They're closely related concepts, but mathematically we determine each one of them differently, okay? So I just wanted to take a quick moment here to make sure that we are not confusing temperature, which is related to the statistical average of all this kinetic energy in a sample, and Q, which is the amount specifically of the heat energy. Okay? All right.